I'm Manas Mandal, a PhD candidate in the Department of Mechanical Engineering. And today I would be talking about the research on using pore former in the anode catalyst layer to improve the PEM water electrolyzer performance. So greenhouse gas emission from combustion of fossil fuels are hypothesized to be the main contributor to the climate change. To decrease carbon emission, renewable sources of energy are being introduced in the energy sector. Due to their intermediate nature, large-scale energy storage system is required. As seen from the figure, the hydrogen holds the capability for large-scale energy storage with wide range of capacity. This hydrogen could be used as a fuel for the electricity production, but also could displace the petroleum from the transportation sector by using hydrogen fuel cell vehicles. It is estimated that the transportation sector consumes nearly 30% of the total primary energy in the US. Therefore, the shift from gasoline to hydrogen could achieve major reduction of the greenhouse gases. And there are many ways of producing hydrogen, but mainly two types using electricity: alkaline and PEM water electrolyzer. A simple schematic of the PEM water electrolyzer shown in the figure. The heart of the PEM water electrolyzer is the membrane electrode assembly, where all the reactions are taken place. The activation losses occurring in the catalyst layer of PEM electrolyzer can be decreased by increasing the specific electrochemical surface area of the catalyst layer. It is hypothesized that carbon can be used as a pore former to increase catalyst layer porosity, and in turn will increase ECSA and the cell performance. Hence, the objective of this presentation is to study the effect of catalyst layer porosity on the electrochemical surface area and the cell performance. So, if pore former is a sacrificial material used to create pores in the catalyst layer, it is incorporated during the ink fabrication and removed after the catalyst layer is fabricated. Anode and cathode, anode catalyst layer were prepared with varying carbon content as shown in the table. SEM images were captured to measure the catalyst layer thickness. The thickness increased with an increase in the carbon content as shown in the top figure. The calculated porosity also increased with an increase in the carbon content, even without corroding the carbon from the cell. This shows that the carbon can be used to increase the porosity. Next, SEM images of new catalyst layer surface shows many microscale cracks without the carbon in it, but no cracks with the carbon. And SEM images of the used catalyst layer surface shows many new cracks formed from the oxygen evolution within the catalyst layer. It appears like a volcano shaped, as shown in the bottom left figure. A higher indentation also is seen with the higher carbon content due to a higher porosity. ECSA was measured using cyclic voltammetry, and the values are shown in the table. It increased with an increase in the carbon content, which might be due to increase in the porosity. This proves the hypothesis that the ECSA can be electrochemical surface area can be increased by using carbon as the pore former. Resistances were also calculated by fitting the impedance spectra obtained from the electrochemical impedance spectroscopy to the equivalent circuit. The high frequency resistance decreased with an increase in the carbon content as shown in the top figure, which might be either due to a higher indentation, which might decrease the contact resistance, or due to the decrease in the electronic insulation due to a higher porosity. And that the total charge transfer resistance decreased due to an increase in the electrochemical surface area. The obtained polarization curves are repeatable as shown in the top two figures for different carbon loading cells. With an increase in the carbon content. Also, the performance of the cell also increased, as we can see the bottom left, bottom right figure, due to increase in the electrochemical surface area, and also decrease in the high frequency resistance, as shown in the previous slides. So conclusion, the effect of the catalyst layer porosity on the ECSA and the PEM water electrolyzers performance was studied using a carbon as a pore former. With an increase in the carbon content, the porosity increased, ECSA increased, high frequency resistance decreased, and the cell performance increased. So this proves that the carbon can be used as pore former to increase the electrochemical surface area and in turn the performance of the cell. Thank you.